All right, cool. So this is on record. So today we'll continue on from what we covered on Monday, which is how does x86 assembly work? Essentially, what happened when you run your program and when you compile your program. So on Monday, we talk about compute instruction. We talk about load instructions such as move, right, which allows you to bring data from DRAM into the register, which is a really, really tiny area where you can store data on the CPU. And then we talk about jump, which we can use to implement if else. So the next, probably one of the most common constructs in every single language is a loop, right? It allows you to run things on repeat. Similarly, basically you can use jump to do looping, right? Basically jump back to earlier part of the code that allows you to repeat the code again with a different value on the register. So this is the repeat of the previous lecture, right? So you can use jump. The letter X here represent what kind of comparison you want to do for the status flag. Is it jump less than, jump greater than, jump uh, greater than or equal, jump always, which means that you always take that jump. And think of this as a similar to the go-to command in C. And again, I don't recommend you to use that particular command at all in the C language, but in assembly, this is okay. Uh, the next concept, now that we cover things like conditional stuff, right? I want you to be aware that there's this concept called conditional move. So we talk about move, right, where we would move data from either the main memory to register or register to the main memory or between register value. Uh, Conditional move basically would do the move if the condition match. For example, you can see here, right? It basically conditional move is C move in assembly. If you have a code that do something like this, if x is greater than y, you would do x minus y. This particular instruction perform x minus y. These blue instruction do x plus y. So if x is less than or equal to y, then you would do x plus y. In this case, you have RAX and RDX being that temporary variable, like this destination, that store both x minus y and x plus y. One thing you can do is basically you can store the results right back to RAX. If you need to do essentially x minus y, so in here, conditional move less than, right? You would move RDX to RAX so that it represents exactly this particular block of code. If x is greater than y, you do x minus y, or you do y minus x, my bad, not x plus y. This is y minus x. Right? So these concept of conditional move in how you design the processor, we call this predicated execution. Predicated execution is exactly the same as you're gonna evaluate the condition, and based on that condition, you decide if you want to do certain instruction or not. And in modern processor, let's say you buy this Intel CPU, it actually consists of multiple stages of execution. That one add instruction actually take multiple cycles. Right? And these predicated execution can be another way you can optimize your program so that it's more friendly toward new processor that has this deep pipeline. So we'll learn about this particular concept, this particular techniques in the computer architecture class, but be aware that this conditional code can allow you to make the program faster. Because at the end of the day, the whole reason why we go through this low-level concepts, why we touch even the C language at all is, can we write a program that is really, really fast, right? You don't want to always rely on Python. And one of the bad thing of programmers in Thailand nowadays is they always rely on Python. So when they need to scale their program to meet the performance goal, they would fail. Like I guarantee you, many software that is coming from Thai company, they fail because of this exact reason. People don't know how to optimize their program. And this is something, this is the gap that I hope that more people are working on a language that are closer to the computer so they know how to actually make things faster. C is way faster than Python. That's one thing I can tell you. Uh, and a few other things is these are what you should not use conditional move for. I'm gonna kind of like put it here. We are not going to definitely cover uh, this in detail for this class, so it won't appear on your exam. But these are something handy to know if you somehow choose not to pursue this direction further. You can kind of refer to back to these slides. There are certain things that you should not do because your code become unsafe. Unsafe means that sometimes you run certain things, it can result in different type of output, right? And the goal of when you want to program anything is you want your output to be predictable. It should, with the same input, with the same program, you should get the same output. You don't want output that have 5 different versions because that way it means that your code have bugs. All right. So let's, is this tertiary operator? So uh not exactly the same. So the question is this ternary operator. I guess you mean tertiary operator, but it's like a different kind of concept. This conditional move, essentially the whole concept is like I have this instruction, and based on the condition flag, the zero flag, overflow flag, uh, uh, the negative flag, and the carry flag, what are those conditions? And based on those conditions, we will either forget about that instruction or would do it. Right? There are two choices. You execute that line of assembly code or just skip that line. That's basically conditional move. Actually, in embedded processor, there's conditional instruction. So basically, every single instruction, add, subtract, everything is conditional. The reason why we have that in embedded processor is it helps with code size. It makes your code a lot more compact. You don't have jump everywhere. You have things like that. You can just have this conditional instruction. That's really prevalent in ARM processor, and ARM processors used everywhere, including your iPhone. Uh, so today, let's switch gear a little bit. Now, let's talk about how do we write a loop in assembly. And for now, I'm gonna give these one program as an example. Population count. Basically, it count the number of. So here's a code in C. It might be easier to go through here, and these are the explanation. Count the number of ones in this argument. Number ones in binary format. So let's say you convert X to binary. How many of that are ones and how many of that are zero? This would output how many of the ones are there. And you can see here, basically the way we do it is you have the result, right? Which is, it's gonna keep accumulating. It accumulates every time my bit, the last least significant bit is a one. And then you keep shifting X. So it would go through every single bit of X. This would be going through this loop multiple times, right? How many times? Depending on how long is this unsigned long, right? So in x86, that is 8 bytes. So it would go through this loop 64 times. And as I said, jump is similar to go to, right? So one thing you can do in C is to rewrite this C code into another C code, but use go to instead of the do while loop, right? So this is the left side is a do while loop. The right side is okay. We're gonna replace that with go to, no matter how I said this is not a good thing. How you do it? You label this line as loop. This line basically is labeled as loop. If you want to loop back, you say go to loop. And you go to loop only if x is non-zero, right? It means that, okay, if you still have x as non-zero because you haven't shipped until the last bits, then you repeat the calculation, go back to the loop. Any questions about this code? Basically, let's say x is this. You would then add and say, okay, zero, you're not adding. Then you shift, right? You shift to the right. You ended up with this, check this bit, zero, okay, you're not adding as well. Then you see a one, you have 0 plus 1 on the result right here. So now result is 1. Then you shift again, your result becomes 2. Shift again, that's a 0, so you don't increment the results. Then you have 1 here, result become 3. 1 here, result become 4. So you return 4. That's basically how this loop works, how this program works. All right, so now we have the go-to version. We have the go-to version on the right side here in this green box. So we're gonna keep this go-to version over here. And let's convert it to assembly because if we have go-to, that's almost the same as a jump instruction, right? So what this program would do is somehow you come into this function, and then over here you know for sure this is a jump. Jump where? Jump back to loop, right? So if you see this part, which is the assembly code, you would for sure see this jump instruction, right? Why? When do you jump? Jump when this is not 0. Same thing as this if condition, right? It would actually stop looping if x is 0. So you jump back to loop right here, this line, if x is not 0. How do you jump into assembly? You mark the loop here, right? This would get marked through this particular uh, symbol. Basically, you put in this symbol. Yep. Okay, so the question is, can I explain again? You don't understand properly. Are you with me on the go-to version in C? The green box. Nope. Okay. So are you with me on this C code? On what it does? That's one loop. Do loop. You do result plus equal x, blah, 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 while x, right, basically means that if x is not 0, you go back to that loop. So you got the yellow side, right? Okay. Then let's convert the yellow thing to the green thing. It's exactly the same program. Instead of do while, we would use go to. How does go to work? Go to basically tell, oh, 0x, you mean here, right? So the question is, what is 0x1? It means the value 1 in hexadecimal. So you can literally write 0x1 in C, and they would know that, okay, that's a hexadecimal number represented for this particular value. So come back to the green box, right? So you have if x means that if x is not 0, that's true. If x is 0, that evaluate to false, right? The only case that becomes a false here is false if x is 0, right? So if x is non-zero, it's going to keep going back to the loop. This line, it means that x, I can't write it here. Give me a pen. Let me actually use the pen. All right, cool. X equal X shift right, shift to the right by 1. You shift that number X to the right by 1. The shift right equal means that it is the same as X plus equal 1, right? X is X plus 1. In here is X equal X shift right by 1. This is right shift. So basically you shift to the right by 1. If X is non-zero, at some point when you shift that enough, everything becomes 0. Right? Everything will become 0. So you know that this loop will end at some point. Once it ends, you return the result. If it's not 0, you go to loop. So are you with me on the green box? Okay, so you have this green box now, right? And we said earlier, go to is, the and, where is that? Oh, this is logical and. Basically, you do you put two numbers together and you do this and, the A and D, like and, right? X and 0, x1. So if X is this, if you do this and 1, what do you get? 0. How about if this is 1, then you get a 1, right? That's it. That's what that particular line do. All right. It's not a pointer. So just want to make sure that's not a pointer dereferencing. I know it's been warning you from assignment 2. This and literally mean that logical operation and. Uh, Basically, these go-to version, as I said earlier, go-to is the exact thing as jump, right? When do we jump? Here, we jump only if we jump back to the beginning of our loop if X is not 0, right? If X is not 0. So over here in this line, right, is this line, basically shift right, SHR is shift right. RDI here is X, right? Basically, this is X. X. If you shift X to the right and the 0 flag is not 1, what does it mean? If I shift X to the right and the 0 flag is not 1, let me rephrase the question. What is the case that my 0 flag would be flipped from 0 to 1? The 0 flag. Flip. It flipped from 0 to 1. 0 to 1 if previous instruction results in the value 0. Otherwise, the 0 flag remains 0. So in here, this particular shift instruction, the only time the 0 flag happen to be 1, it has to be that once you finish shifting, right, X becomes 0. That's the only case that the 0 flag will be 1 and jump not equal. This jump not equal instruction only jump if the 0 flag is 0. If the 0 flag is 0, you go back, X is non-zero, right? X is non-zero, which means that this 0 flag is 0 because X is not 0, which means that you jump. Otherwise, you're done, return. RET is return. You go back, return the value. These and instruction correspond to this and. Add instruction correspond to this add. Right? Basically, you and X with 1. Then you add results with the result of this. So the result of and is here. The difference between EDX and RDX is how many bits there are. How many bytes is that? EDX is how many bytes? 4. RDX, I mean, RAX, my bad. RAX, I mean, EDX is 4 bytes, RDX is 8 bytes. And then you add RDX, which is the result of these and, right? This is basically RDX. This is RAX. So you add them together. X is RDX, result is RAX. Then you keep shifting and you got at the end of the day, you got the exact same function here. So this green box corresponds to this assembly code. If you're confused for now, I'm gonna give you the whole view again so that you can watch the video again. Basically, in here, the key point is the jump, right? The jump instruction, which behave like a loop. Where do you jump to? You jump back to the beginning of your loop. When you jump when x is not 0. It just happened that these two assembly code, if you go back do it on the paper, you see that the only case you will not jump and return the results is when x is 0. What is x? RDI is x, RAX is the return value. So if you go down to your code, if you see something with dx or di, that is essentially x. If you see something with ax, that's results. If you replace those letters with either x or results, you see that this is the same particular code. It's just the name of register has to be something in this format. When you jump back to this label to L2. This is the destination of your jump. Okay, so if you are still confused, office hour, I'll be here afterward for an hour. All right, so that we can proceed on as well for another type of loop. Basically, jump would behave like that condition check plus go back to the beginning of my loop. The rest is within the loop body. This is the general version of do while loop. Right? In general, if you have a code like this, you have the beginning of the loop, you have something that you're doing, the loop body, and you have some testing condition. The go-to version is something basically similar. You have the body of the loop, that's the beginning. This is the do, right? And this is while this is true. You go back here. And then the body is just a bunch of code. So now we cover the do while loop. You jump back to the beginning of the loop with the condition check. How about the while loop, right? So generally there are 3 types of loop. We cover the do while loop. The next type of loop is the while loop. In C, as I said earlier from Monday, you can actually see your assembly code by using obj dump. One thing that you need to do while you're compiling is you need to make sure you put in this -og. That -og would make sure that the while loop is represented in the way we are teaching you right now. Typically, what happens when you compile your code is the compiler, the GCC compiler, trying to make sure your code is as fast as possible, which means that sometimes they would actually break the loop into the straight line code that happens. the dash OG would prevent that. So you can still see the loop body on the assembly code. Basically, if you have a loop like this, C code, right? The yellow box is always the normal C code. You can convert into a go-to version. The green box for this lecture is a go-to version of the C code, right? So what does the while loop do? The first thing you do is you check the condition. Right? You check if this is true. So the go-to version essentially begin with go to this test, right? Test if this is true. If it's true, you go back to the loop body. If this is false, you go down because it's done. That's essentially how you can convert a while loop into the go-to version. Once we have the go-to version, we can convert that to assembly. So let's use the same example. Population count. We have the same thing here, right? But now we change from do while to a while loop. You start with while x. You have the loop body, so this is the loop body. And this is the end of the loop. This is the go-to version. The first thing you jump to is right away, you go to test. Test if x is 0 or not, right? So you go to test. This is check if x is 0. If x is 0, go return the result. If x is not 0, jump back here to loop. Loop. Once you finish the first iteration of the loop, you then test again. If you test and x is not 0, you jump back to the loop again. Otherwise, you finish the loop, comes out of the loop. And here's the conversion. Basically, you have this while loop, right? You can now, without the dash OG, if you use dash O1, which is a different form of optimization, right? This allows you to rewrite the code in the compiler. It would rewrite the code from the while version of the loop into this do while version, right? This while test and then the body of the loop is essentially if test is not true, you're done. You don't have to even come into the loop. If x, if test is true, then you run the body of the loop, right? So if test is not true here, go to done. Otherwise, you do this do while loop. So you see, this is a do while loop. If you have this do while loop, this can be convert back to the assembly version of do while loop, right? From the earlier example. So you can change your go-to code here again. If not x, finish. If x is not 0, if x is not 0, you go into the loop. If x is 0, done. When you're done, you return the result. But then before you end the loop here, because now it's in the do while format, you have if x go to loop. So if you look at just this part of the code from this line to this line, this is the exact same code from the do while example. Right? It's the exact same code from the do while example we have earlier. Which means that the assembly code for these block from loop to before right before done is the same thing as the assembly code we see earlier. Right? And then you're gonna have another line of assembly code that say if not x, go to done, and over here it just return in assembly. So once you can convert a while loop to a do while loop, then the assembly code would work the exact same way. You replace that code you see earlier on this block right here. Then you write one more line to perform this check, and that's it. So let's cover the last part of a loop, right? You have seen do while, you have seen while. Now let's do a for loop. How does for loop work? You have the initialization, right? Then you test, and then you update, right? It's a three-step thing. This is the C code, right? That have the exact same function implemented in a for loop. It starts with initialization, I is 0. If I is less than the word size, right? What is the view size? It's size of int multiplied by 8. Basically, how long we want to test for x, right? At the end of the loop, you do this update. And here's the body of your loop. Each iteration, you would shift x to the right and add the result back to summarize how many ones are in the input x. So basically here you can convert the for loop into a while loop, right? Why is that the case? For loop is the exact same thing as a while loop, except for you have this in it. At the beginning, do this first. For loop is exactly as the same as while loop, except you have init and you have the update at the end. So you have this part and this part. So if you know how to convert a while loop into a do while loop into the assembly, then you can convert a for loop into a while loop that has initialization and update. And then that get converted to a do while loop, which will get converted to assembly. So here is the example, right? You have three little box here. This is init, right? This init, this is test, this is the update. So those are the three different things you need to do in a for loop. And the last part is just the loop body. Let's convert. So this is the C version without go-to. What's the difference here? We replace the loop from the for loop to a while loop. Okay, so you have this I equals 0 right here. You have I plus plus at the end right here. The loop body goes in here. Then this test, right, goes into here. Now you convert for loop to a while loop. With this while loop, we can actually change it into a go-to version, right here. So this is for loop. This is go-to. This is the go-to version on the right. You can see that this is the initialization. You assign I to be 0, right? This is the in a do while format, right? So if I is less than size, and you have the not here, basically uh, if x is essentially 0, you're done. So here you finish the execution. This part is the loop body. Over here you have the not test, right? Over here. This is the condition check, right? If this is true, you go back to the loop body. If this is false, you fall down to this done. This is the part where we update I. So that basically cover initialization, testing, and update, whatever you have to do at the end of the for loop. And then, size underscore t, wait, where is that on here? It's a basically it's a data type that represents a size. size underscore t is a data type similar to int, similar to long, but it represents a size of a data. So for example, you can use size underscore t to store something like how long is my array, how long is a struct, how long is an integer. Treat it as another data type, essentially. But the purpose of that, conventionally, you would know if your friends write the code this way, you would know that I would store a data that are related to the data size, not not the data you want to compute, but it's something related to the size of your data. All right. And here, one additional thing that the compiler would do, because you have I equals 0 and W size is definitely not 0, it would actually eliminate that line in the assembly code. So if you take this code and compile it, you might not see the assembly code that correspond to this line. Why is that the case? Compiler do things called date code elimination. Basically, it means that if GCC, if the compiler detect that that line of code would never get executed, it will get rid of that line for you. That's what it does. That's why sometimes your program can run a little bit faster or compile and result in something a little bit smaller. This is coming from the code elimination. So in summary, right, we have do like if then else. So this is basically jump. You have the do while, which convert to go to, which then convert to jump. Right? You have the while loop and for loop, which will then convert to a do while, which then convert to a go to version, which afterward you jump in assembly. Inside the assembly, the way you control code movement, how you would run your program is through conditional jump, conditional move. This is something we'll cover next. This is useful for a switch case. And then the last bullet point where we say compiler generate code sequence to implement more complex control. Those are the advanced compiler techniques that can allow them to modify the code. You get the exact same result. Everything is correct, but your code looks different. And there are techniques and there are theory behind it where you can actually shuffle the code, replace something, get rid of some part of the code, and you get something that runs faster. The standard technique, as I said, everything is convert to do while. Everything is convert to do while loop. All right. So I talk about this jump table, and let's now dive into this. Right. How about switch case? That's another special condition kind of thing that you can implement in C. Right. For example, if you have a code like this, what am I checking? What variable that I'm checking to see which of these case I'm running? X. That's so everyone see that we are checking X right here. All right, long pause. Hopefully everyone catch up now to where we are. Switch case. We are trying to check what is the value of X. Based on the value of X, we would do one of these cases. If you have to break, it means that you do this case, jump to done. If you don't have the break, see, in this case, you would then do W equal Y divided by C. Then you would do case 3 because you don't have the break. So you do W plus equals C before you go back to done. There's also multiple cases. So if x is 5 or if x is 6, it would do the same thing. It would run this line. This is if x equals 5 or 6. Otherwise, any missing cases, that go to a default case. Okay? The default case is when w is 2. Any questions about this particular block of code? So there are 3 different types of the case. There are share case, like if x is 5 or if x is 6, you would do the exact same instruction. If x is 2, it would fall through, so it would execute that line, then it would do another line of code that is in case 3. Then you have the default case. Yep, so the default means that if x doesn't map to any one of these cases here, all right, so a common setup for a switch case is you are going to jump a lot, right? Because there are multiple points that you're going to jump to. If x is 1, go here. If x is 2, go here. If x is 3, go here, etc., etc. These can be implemented by something we call an indirect jump through the jump table. So you have this switch case function, which is from the previous example. We don't have the room to fit out the code in here on this slide, right? And let's make this assumption. The argument x here, x is in REI, y is in RSI, c is in RDX, and then the return value would be stored in RAX. So this is the assumption we're going to make in this example. All right. RDI is X, RSI is Y, RDX is C. If you compile your code, this is something that you can potentially see. It would jump to this random location, and that random location would have a different set of values. This is called indirect jump, which is something I'm going to show here. RCX. That has okay. So that has to do with how we call a function. It's a totally different thing we're gonna cover at the end of this class. It happens when you need to call a function. Are you with me? Basically, slightly unrelated to the jump table, but it's something you have to do because the fact that you only have 16 register. So I'm gonna cover that once we cover the switch case example here. Just forget that RCX exists. It's something you have to do. But so let's discuss this concept called indirect jump, right? So from the earlier example here, you see the first thing my code would do is jump to L8. I don't know where L8 is. Somehow you're gonna jump there. And then you see that L8 would be basically something called a direct jump, right? And then L8 would contain multiple location where you can jump to based on X. And this is something you can see in a switch case. It's implemented through direct jump. Basically, for each of the case, you have the direct label, L3 or 4 or 5, and they'll jump based on the value of X. A more efficient way in C code, they actually can do it through indirect jump. What happens if you have indirect jump is something like this. Jump L4 RDI8, right? And what is L4? L4 is somehow is a location that only store where do you jump next. It's a location that store where do you jump next, and how do you know where you're going to jump, right? You notice that x can be 0, 1, 2, 3, 4, 5, 6, etc., right? It can be this sorted value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, blah, blah. So you know that this is something you can do. You can jump, oops, starting from L4. L4 is our offset, right? So this is the addressing mode. If this is X, RDI is X, what is this block of addressing mode do? What am I calculating? We are calculating, first of all, the location of L4, right? Plus, what is our base? The base, recall slide from Monday. The base is whatever is going here, right? What is there? It's nothing there, right? It's nothing there. So what's the value of our base? If nothing is there, the value is 0. Plus, what does this mean? What is RDI? RDI is X, right? What is 8? What does it do to RDI? You remember you have the D, right? Plus RB plus RI multiplied by S. Yep. So you multiply X by 8. Why do you have to multiply X by 8? In a 64-bit machine, how big is my address? A 64-bit machine, I need to represent one single address value. I need 64 bits. What is 64 divided by 8? 8 bytes, right? So each address would need to take 8 bytes. Right? Are you all with me? Basically, each address is 8 bytes, which means that if I want to differentiate between the case of jump here if x is 0, jump here if x is 1, jump here if x is 2, jump here if x is 3, blah, blah, blah. Okay, again, please. All right, so let me explain it again. Let me find but you got this, right? You got this equation that comes from this part. This part convert to this. Okay. That part tells me where do I jump to. These are the locations we want to jump to. L8, L3, L5, blah, 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 right? Why is that the case? Because we always start with L4. Because we always start with L4 and we mark L4 is right here. L4 is right here. This is an assembly code somewhere. It will be in the code somewhere and we'll have this exact line. It's a L4 start here, Q quad, and align 8 here means that I'm gonna align whatever down here into a block of 8 bytes. A block of 8 bytes. Why is that the case? Because L8 is a location of your code, right? It's a location somewhere in the memory that represents a program. L8 is an address. L3 is an address. L4 also is an address. Everything here is an address. So what it does is you have L4 right here. It's a table. That's why we call this a jump table that consists of multiple slots. Each of these slots represent the function that we want to jump to, which is function is a part of the program. It has a starting point. That starting point need an address. Right? Basically, if you need to start, say, I give you an address and I say, go there, that's where you start. You need an address, right? You need an address to be able to go there. So L4 is a table. In there is stored the location of L8, location of L3 based on this table. So this table convert down here, right? Location of L5, location of L9, location of L8, location of L7, and then L7 again. And these block are 8 bytes. Basically, it means that you need 8 bytes inside DRAM to store these things, right? And when you have this equation, you start from L4. You start from L4, which is you start right here. Right? You start right here. Based on the value of x, which one am I pointing if, let's say, x is 2? If x is 2, which one of these I'm pointing? Is it L8? Is it L3? Is it L5? Is it L9? Is it L8? Can someone tell me the answer? L5, yes. Why? Basically, you replace x by the value of x, right, in this equation. Yep, and then you plus by 2 times 8. Basically, from L8, if x is 0, it's point right here. This is what happened when x is 0. If x is 1, you have L4 plus 8. L4 plus 8 is the next entry right here. If x is 2, L4 plus 16 would point right here to L5. If x is 5, for example, then L4 plus 40 would point right here at L7. If each of these blocks is 8 bytes long, x would the value of x would give me the exact label. Is it L8, L3, L5, L4, L9, L7 that I need to jump to. That's why it's called a jump table. And here is the kind of like the abstract overview of this, right? You have the table that I showed earlier. This is the table from the last slide, right? That have L3, L5, L7, and all those things. Each of this is mapped to some part of the code. Then when you have X, which is the input to your switch case, right? Based on this value, it would jump, say, here. And then it was like, okay, that's my target. So I'm going to jump here to this code block. So you know exactly which code block you're going. In extended C, you can use this thing called jump table. It represents something exactly like this. And now I'm going to switch back to our example, which is a switch case. It's a switch case. So you see, this is the example earlier. You still remember that, hey, if x is 2 and 3, that falls through. If x is 5 and 6, that's share the same condition. If x is 0, 4, 7, and anything more than 7, you go to default. Now, if we mark L8 right here, what are the different cases that we go to default? What are the value of x that we go to default? 4. Perfect. Yeah. So basically, in our jump table, you can put L8 here and here. What are the cases that we would go to 7, 5, and 6, right? So you put L7 right here. And if we label this case tree as L9, you can put L9 right here. If this is L5 for case when x is 2, you put L5 here. You put L3 here. For the case when x is 1, you can then put the L3 in our jump table. So from our assembly code, right, jump above, what does jump above do? Jump if our x is above whatever this value is. When we have compare 6 and x. If x is anything greater than 6, go to the default case. Which is L8. That's a default case. Which also happen to be the same case as here, right? When x is 0 and 4. So if x is 0, 4, or anything above 6, which is 7, 8, 9, 10, 11, blah, 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 go to L8. Otherwise, use our jump table. Use our jump table, which is this thing right here. So it knows that, okay, if the value of x is 2, go there. In the next slide, I will show you a more detailed example of these exact same code, right? This exact same switch case, but in assembly. Which is this thing here. I'm gonna explain one at a time. All right. Let me ask you one question. Where is that indirect jump? Which line is that? This is our indirect jump. Right. Let me go back from to an earlier slide right here. Right. You have indirect jump to L4 with some offset. Before that, you have the jump to the default case, which is jump always. Right? So you can see here, before this line, you have jump always. So this is the default. And if it's a default case, you go to what address? You go to which line? Actually, you go to which line? What is the address of my default case at the end? 400614. That's actually close. Do you mind if I go back to our code, C code? Basically, our C code, the default is you need to do one more thing. You need to do W equals 2. Right? So in here, by default, assign true to W, the return value. How can I say it's exactly that line? Have it here. Say, okay, if you're going to the default case, go to that address. And where's that? Where's 400614? Right here. This is default. Okay, so are you with me on the default case? Because then we'll go into the rest of the case. All right, again, please. Sure. So in a switch case, right, the first thing we need to cover, the first thing that assembly code would handle is, okay, what's my default case? If x doesn't map to anything here, do this. This is a jump always, right? This particular line, not jump always, my bad. for some reason. Sorry, it does not jump always. JA is jump above. Jump above. It jump if my input. So here, this is X, right? If X is greater than 6, if X is greater than 6, go to that line. How can I tell what line is that? The line is the number that comes right after jump always, which is 400614. 400614 is the assembly line that I'm going to jump to. Where is 400614? In this block of code, right here. Right? You just look to the left. The left is the address of that instruction. That instruction would be on that address in DRAM. If you look at DRAM and you look at that exact byte, you see that instruction. Basically, it's right there, and you see these byte B8 02 00 00 000. So that's when X is greater than 6. That's the default case. Now I'm going to go over to our jump table. So what is the address of our jump table? So this is the instruction for the jump table, right? This is the address 0x4007F4 plus some value based on X. But the first entry, when X is 0, it will definitely be at 4007F0, which I'm not showing it here, but I'm going to show it on the next slides. Okay. Where is 400X0? So here is the value that you will see. So if you go to 4007F0, which is right here, if you go to GDB and print out what are the value around that, you see these 8 different values. So which address correspond to the jump if X is 0? So let me do some leveling, right? So let's say this address is A, this is B, this is C, this is D, E, this is F, this is G, and this is H. If X is 0, do I jump to A? Do I jump to B? Do I jump to C, D, E, F, G, or H? Which one am I jumping to? If X is 0. All right, go back to that table, right? This is L4, right? L4 is 4007F0. This is if X is 0. So what's in there? A, yes, exactly. So you go to A. What is A? 400614. I'm gonna go back to the earlier slides to see the assembly code. What is, yeah, it's a default case. So if you look at 400614, right here, right here again. Right here. So that's when X is 0. If X is 1, right? If X is 1, you go to B, which is 4005F0. This is when X is 1. What is 4005F0? Let's go back again and see what is that code. Right? So let's go here. Right here, right? 4005X0. So you go here if X is 1. What is that? You do move and multiply. Basically, the exact same code we have in the switch case when x is 1. Afterward, you just return, right? Return, because you're done with the function. For x equal 1. Let's come back here. If x is 2, you would go to 4005F8, which is right here, right? And as you can see here, this is the line right after the return when x is 1, right? So you now should get the picture. Basically, this table would give you the line that you need to go back to based on the value of x. Based on the value of x, you go to that line. Can someone tell me why do I get garbage over here? That's definitely not on the code that we have. Out of range. Why is that the case? So you go to A if x is 0. You go to B if x is 1. It is, yes, exactly. It's just a random memory. It's just some junk inside your DRAM. Or it might be your friend's data. It might be another program's data, or it might be just this program's data as well, right? But it has nothing to do with this jump table. Why? G is when x is 6. Right? G is when x is 6, and we already established here, right, that if x is greater than 6, you go to the default case. So you don't even need to build the table for anything that is greater than 6. So these slides show you, okay, in the case where x is 1, in the case where x is 1, this is what you do. Move, multiply, right, because it's basically w equals y multiplied by c. So you would then first get the value of y, then perform the multiply, which is y multiplied by c, and return. That 3 lines, so mark these 3 lines here. If you go back to this code, it's the exact 3 lines that we see between 5F0 to 5F7. Right? It's the exact same 3 line. Now, in the case where x is 2 and 3, so if you want to compare this to the slides that we seen earlier, this is a little bit interesting. And I'll tell you why. First of all, if x is 2, you do w equal y divided by c. If x is 3, you do w equals w plus c. What happened is when you compile this code, the C compiler would detect that, okay, you can actually optimize this code a little bit. So when you have to do this fall through, once you finish with case 2, right here, you then go here. But if these two things have to share this value w, if they have to share the value w, you need to initialize w here. For this case, because you have this long w equals 1 right here before you begin the switch case. Right? Before you begin the switch case, if x is 3, basically w equals c plus 1. If x is 2, w then first equal y divided by c, and then w equals y divided by c plus c. So let me write it so that it's clear. If x is 2, right, this is what you do. W equals y divided by c. Then W equals W plus C, which means that this is why I divide by C plus C. Right? That's if X is 2. If X is 3, this is what you do. W is 1 way back in the beginning. So this is W equals C plus W, which is the same as C plus 1. Right? So in the case that X is 2, you first need to run this, then you jump right away to here. Otherwise, you then need to reinitialize, because you can't just do jump if you want to fall through, which is right here. You do the W equals 1 right here. This is the merge. This is the Y divided by C that I showed earlier. This all everything here is just to make sure that this initialization doesn't impact the two cases that are falling through. And then you see that this is the exact same code from our assembly. Back a few slides ago, the big table with the assembly code. All right, so let's cover the last case where the two cases jump to the same place. This is simple, right? Case 5 and 6 go to the same place. So if you go back, so let me go back to that jump table. You notice that F, which is when X is 5, and G when X is 6. They go to the same address. Why? Because they have to do the same thing, right? They go to the same address, which is right here. Which means that both if X is 5 and 6, they would run that code and return. If you recall the case where you have 2 and 3, you'll see that this is the merge. This is the assign when you have W equal 1. This is the case 3. So this is basically the beginning of case 3. And this is both shared by case 2, 3. You see that this jump to 607, which is right here, right? Right here. So case 2 would skip this move. It would skip this move, jump right to this add. If you have X is 3, you would first have to do the move and the add and the return. All right. So that's it for switch. Basically, it usually uses this jump table, and the jump table will tell you where you're jumping to depending on the condition, right? And if you have a large switch statement, you would use jump table, but keep in mind that if you have something like this, switch X, and then case 1, case 1000, case 1,000,000, and default. If you have this and you use the jump table, how big is your jump table? How many entries do you have to have? You need to cover the 1,000,000 case, right? Which means that you need to have 1,000,000 and 1. That's a huge table just for this only 3 branches. So if that's the case, ECC would convert this into if else, if else, if else, if else. That's all. You would have to have this conversion from jump table to if else statement. All right. And we do have another block of material that relate to function calls. But let's not do it now. Let's go to our in-class exercise so that I can do a Q&A as well as trying to clear up some of the possible confusion that I think many of you have right now. So let me switch back to Discord on my desktop. That way everyone can ask the questions, and let me jump to in-class exercise here, right? So we will also do along the same way. Let's practice binary arithmetic by calculating the parity bits, which means that we're gonna count the number ones and zeros in your code. Right now, I have make 5 different links here from collab edit. You pick one of these 5 so that you have multiple groups that can work on this exercise together. And I'll actually switch between all 5 of this. Give me 1 minute to set up. All right. And in the meantime, I'm gonna set up everything so I have my keyboard back, so I have my mouse back, and then I have all this collab edit. That's the end of today's new material. The rest will be Q&A. The rest will be about the topic that we talk about today. Let me save everything, including this recording.